Welcome to Amino Acid Metabolism Part 2. The two amino acids, glutamate and glutamine, provide a critical entry point into our organism for reduced nitrogen. Glutamate is the source of amino groups for most amino acids, while glutamine is the source of amino groups in a wider range of biosynthetic processes. So to relate this statement to the flowchart here, glutamine tends to go this way, glutamate tends to go this way. Now we focus on a reaction called transamination. Reactions called transaminations are involved in transferring amine groups between biomolecules. These are reactions that simply takes an amino group from a donor molecule and place it onto an acceptor molecule. Transamination processes are of course catalyzed by enzymes. These enzymes are called transaminases. Now, glutamate is the source for amino groups for most amino acids that are being synthesized. And as previously stated, glutamine plays the same role in a much wider range of biosynthetic processes. Now, part 2 of this lecture, where we're currently in, will concern the biochemistry of the processes indicated by the glowing red sphere number 2 here on the flow chart to the left. In part 3, we will discuss how nitrogen atoms from our amino acid pool enters our metabolism in the form of ammonia. This will be this part of this flow chart. But for now, we will focus on this part of the processes. So first we will look at the aminotransferases, more specifically the alanine aminotransferase. As long as the glowing red 2 is on the slide, we stay with the transferases and the amino acid metabolism that they are related to. And remember the overview scheme in the previous slide. Aminotransferases are active in both muscles and the liver and acts on pyruvate, alanine, glutamate, and alpha-ketoglutarate. All of them are chemically close to each other, as you will see when you inspect the structures that are shown here. For instance, notice the chemical structure of pyruvate and compare it to alanine. As you can see, these compounds only differ at the carboxylate amine position. Sorry, the keto position and the amine position. The transferase simply converts pyruvate into alanine by donating glutamate's amino group to pyruvate. Notice that the pyruvate comes from the glycolysis. It's essentially half of a glucose molecule, and this connects the amino acid metabolism with the citric acid cycle. So alanine is very easy to synthesize. You just need glutamate and glucose, and then you create pyruvate and you join them up with the reactions as shown here. So alanine and alpha-ketoglutarate, they then enter the bloodstream and are transported to the liver. And here the same enzyme catalyzes the reverse reaction, transferring alanine's amino group to alpha-ketoglutarate. So the equilibrium constant of this reaction is about 1, meaning that the direction can be changed depending on the concentrations of the substrates and the products. In the liver, conditions and regulation favors the production of glutamate and pyruvate. Alanine aminotransferase uses a prosthetic group called pyridoxal phosphate, or PLP. And as we go to the next slide, we will take a closer look at that enzyme and its active site, including pyridoxal phosphate. So the structure we see here is from one monomer of the dimeric aspartate transaminase from E. coli. The pyridoxal phosphate prosthetic group is shown in the middle as spheres of blue and red. Transaminases are also called aminotransferases and comprise a group of many enzymes several with alpha ketoglutarate as acceptor of the amino group transferred. They are named from the donor of the amino group, so in this case, it is the aspartate who donates its amino group. The reaction is organized as a ping-pong reaction. This means that the donor must leave its amino group in the active site attached to pyridoxal phosphate, then it has to leave. Then the acceptor comes in, occupies the active site, and pyridoxal phosphate hands over the amino group to the acceptor molecule. Now, let's look at the reaction and this reaction and the active site. So, pyridoxal phosphate is a chemical substance that is quite close to vitamin B6 and is used as a temporary anchor for the amino group to be transferred as the enzyme waits for the acceptor to occupy the active site. It reversibly transforms between an aldehyde form to the left and an aminated form to the right. You can see the group that changes highlighted here in pink. It then donates the amino group to an alpha amino acid and converts back to its aldehyde form. Pyridoxal phosphate, PLP, is bound through non-covalent interactions and covalently through an aldimide or a shift base linkage of a Lys residue at the active site. This is shown here. Although I showed the enzyme as a monomer in the previous representation, it is in reality a dimer, as shown in the top right of the slide, with chain A in blue and chain B in light blue. So at the bottom left PLP, the prosthetic group, is shown in a close-up of the active site. So at the left or at the bottom here, and the left of these two pictures, we see PLP within the active site. You can see it's quite a snug and tight fit there. Here it is in its shift base form. Now next to it here, it is shown bound to a substrate analog in green, and this provides a plausible snapshot of how a real acceptor might be placed in this pocket. In reality, it's very hard to capture the situation with a real acceptor molecule because they are so quick to move in and out, so you will not be able to determine the structure while it's in the place. This analog goes into the binding pocket and binds in what we have to assume is a similar way to the real situation. PLP is a very versatile compound, allowing it to be involved in several types of processes in the organism. Please do not be daunted by the seemingly complex reaction schemes shown here. On this slide, we will just use the overview here to gain an overview, and we will only discuss general outcomes. So PLP has chemical abilities that allows its versatile use in many reactions. So its key chemical abilities are: 1, to alternate between binding the enzyme and binding to the donor and acceptor of the amine group. And 2, the ring structure it has here allows it to move electron pairs around. You see all the double bonds here. These represents electron pairs, and the double dots here also represents electron pairs, and chemical change can be understood as the movement of electron pairs, at least in these reactions shown here. So the red arrows on this figure indicates how electron pairs can move from one position to another position on PLP. And finally, ability 3 is that PLP can also form resonance structures, which help stabilize intermediates and help it act as an electron sink. So as electrons come in, or change place, that can destabilize the compound. But if you have the availability of resonance structures, this helps stabilize the intermediate and bring the process forward as the resonance shifts from one to the other. So these chemical features allow it to be involved in transamination, that is scheme A here, which we've already talked about. It can also be involved in racemization, scheme B, which converts the compound into its mirror image with no other change. So there is not a chemical change as such, it's just converting one mirror image to the other mirror image. And racemization is then a randomization of mirror images. So if you have a mix of only L amino acids and they are racemized, then in the end you will have 50-50 of each. We will not go into more detail on pathway B and C here. However, on the next slide, we'll briefly go through pathway A, transamination, because it's importance for the pathways that are discussed, especially in chapter 18 of Leninger. This reaction pathway is the same as shown on the top of the previous slide, but with more detail. So the reaction starts at the left with the pyridoxal phosphate being bound to the enzyme through an internal aldamine bond. Going from left to right, we get a donor amino acid that binds in the pocket in a way that lines up the reactive groups like this, or here first. Notice then how electron pairs shift from the top here, the substrate, and towards the Schiff base intermediate. So we have a domino effect here of electrons coming in and a reshuffling of the double bonds on the Schiff intermediate and the ring structure. This intermediate will rearrange and kick out the proton. And this is the resonance form, which allows this intermediate to survive for a while until it can shed the proton, further stabilizing it. So in the final step here, the active site takes a water molecule from the solvent to hydrolyze the connection between what will become the alpha keto acid and the pyridoxamine phosphate. This compound can again form an internal aldamine bond with the enzyme, as shown here in the first leftmost structure. All right, brain full, I guess. That's okay. Let's have a break and return to the next installment when you are ready.